Good morning, everyone. We are here to discuss about Chapter 10, Statistical Inferences about two populations. The reporters for this topic would be yours truly, Mr. Jonell, Mr. Cedric Diaz, Mr. Mark Lazaro, and Mr. Ronald Renison. So, the learning objectives for this topic is to test hypotheses and develop confidence intervals about the difference in two means with known population variances using the statistics, two means of independent samples with unknown population variances using the t-test, two dependent populations, two population proportions, and test hypotheses about the difference in two population variances using the distribution. I would be discussing the first topic, which is hypothesis testing and confidence intervals about the difference in two means using the statistics. When can we use this type of test? We can use this type of test when the sampling plan calls for selecting two independent samples, calculating the sample means, and using the difference in the two sample means to estimate or test the difference in the two population means. Or if we wanted to determine if the samples came from the same or a different population. For example, are two brands of toothpaste equally effective? Do two brands of tires wear differently? Or does an aluminum produced under two different temperatures have the same strength? The formula for the difference in two sample means is as follows. Z is equals to the quantity of the mean of the sample 1 minus mean of the sample 2 minus the quantity of the mean of the population 1 minus mean of the population 2 over the overall square root of the variance of the population 1 squared over the number of samples for population 1 plus the variance of population 2 squared over the number of samples for population 2. To illustrate, suppose you want to conduct a hypothesis test to determine whether the average annual wage for an advertising manager is different from the average annual wage of an auditing manager, where your advertising managers would be your population 1 and your auditing managers would be your population 2. So your null hypothesis would be the average salary for advertising managers would be equal to the average salary of your auditing managers, and your alternative hypothesis is that their salaries are not equal. A random sample of 32 advertising managers from across the United States is taken, and a similar random sample for 34 auditing managers were chosen. The sample of advertising managers has a sample mean of 70.700 and a known population standard deviation of 16.253. The sample of auditing managers has a sample mean of 62.187 and a known population standard deviation of 12.9. Let 0.05 be your significance level, giving a z-value or confidence value of 1.96. To compute for the critical value, it would be 70.700 minus 62.187, which is the mean of both samples, which is your auditing managers and advertising managers, minus 0, since we are not provided with the average salary for the whole population, divided by the overall square root of 16.253 squared over 32, which is the population standard deviation and the number of samples for group 1, plus 12.9p squared over 34, which is the standard deviation for the population and the number of samples for group 2, which would give you a result of 2.35. Since 2.35 is greater than 1.96, this is outside of our acceptable region. Hence, we can reject our null hypothesis and conclude that there's a significant difference in the average annual wages of an advertising manager and an auditing manager. Based on the figure presented, acceptable critical value will only be from the range of negative 1.96 to 1.96. If the critical value is outside of the range of your confidence level, it would result to a rejection of your null hypothesis. Another test is the confidence interval to estimate the difference between two means from population. This test is used to determine the range of the difference of the means of two population groups or the range of the means of two populations. So the formula would be the quantity of the mean of sample from population 1 minus the mean of the samples from population 2 minus your confidence level times the square root of the variance from population 1 squared divided by the number of samples from population 1 plus the variance from population 2 squared divided by the number of samples from population 2. On the other side of the formula, you would just change the subtraction sign to a addition sign in order to compute the confidence interval. So to illustrate, suppose a study is conducted to estimate the difference between middle-income shoppers and low-income shoppers in terms of the average amount saved on grocery bills per week by using coupons. Random samples of 60 middle-income shoppers and 80 low-income shoppers are taken, and their purchase are monitored for 1 week. The average amounts saved with coupons as well as sample sizes and below standard deviations are in the table below. Construct a 98% confidence interval for the difference between the mean amount saved with coupons by middle-income shoppers and the mean amount saved by coupons by low-income shoppers. So the z-value associated with 98% confidence is 2.33. So to compute 5.84 minus 2.67, which is the mean of the samples from middle-income shoppers and low-income shoppers, minus 2.33 times the square root of 1.41 squared over 60, which is the standard deviation and number of samples for middle income shoppers, plus 0.54 squared over 80, which is the standard deviation and the number of samples for low income shoppers. And then on the other side of the equation, you would just replace the subtraction sign to an addition sign. It would give you a result of 2.72 greater than or equal to the difference between the mean of the population less than or equal to 3.62. There is a 98% level of confidence that the actual difference in the population mean coupon savings per week between middle income and low income shoppers is between 2.72 and 3.62. We can test hypotheses about the difference in two population means using the z-test via Microsoft Excel. However, Minitab cannot support this type of test. Shown below is the sample test performed using Microsoft Excel. So that ends my report.
Thank you, Sir Jonell. Good morning, everyone. So the next topic would be topic 10.2, hypothesis testing and confidence intervals about the difference in two means using the z-score statistic with independent samples and population variances unknown. So let's start with hypothesis testing. So a population standard deviation are not known, but the samples are independent and the population is normally distributed. The t or test distribution can be used. So the formula for the test is presented. So it seems a little bit complicated, but we just need to understand and to identify the values of each of the statistical signs, and then we will just be substituting it afterwards using this formula to arrive at the answer. So let's take an example for us to absorb on this formula. So at manufacturing company, there would be two groups of sample for the training. The first group would be composed of 15 newly hired employees, which will take the traditional method of a 3-day lecture followed by a question and answer session. On the other hand, there is a second group, which is composed of 12 newly hired employees, which will take a 2-day DVD lecture and without any question and answer session. So there is a test scores which have been presented on table 10.2, which are the scores on the training method A and training method B. So let's start on a step-by-step procedure to properly substantiate our example. So the step one, the hypothesis for the test is currently presented. And since there's two hypotheses, this is a two-tail test. Step two is the assumption that the scores are normally distributed and the population variances are equal. But since the variants are not known, the test distribution should be used. The third step would be the value of alpha has been chosen to be 0.05. So as we all know and we have learned, alpha is the probability of rejecting the null hypothesis. So it pertains to the significance level or the confidence level. And in this case, the confidence level was identified to be 95%, which will give us an alpha value of 5% or 0.05. So since this is a two-tailed test, the alpha is needed to be split into two, which will yield to 0.025. And then we need to identify or compute for the degrees of freedom, which is quite easily to understand. We just need to add the number of samples, which is 15 and 12, and then less by the constant 2, which will give us 25. So then we will just need to get this 25 degree of freedom with a 95% confidence level which will give us a 2.060 critical value for t. Then on step 5, we just need to identify some of the additional values of the statistical signs. First would be the number of samples. It's 15 and 12 respectively. Then the mean, which we have already learned how to compute. It's just the average of all the test scores, which is 47.73 and 56.5. Then we need to compute for the variance and the standard deviation, which is identified to be 19.495 and 18.273. So we'll just be using all the numbers which we have arrived and substitute it on the formula which I have previously presented, and will give us a value of negative 5.20. So this value is less than the critical p-value, which is negative 2.060. So the null hypothesis will be rejected. There is quite a significant difference in the mean score of the two tests. On step 8, we could already form a conclusion. So the managers can conclude that there's a significant difference in the effectiveness of the training methods. So upon examining the sample means, they realized that method B, the two-day DVD method without the Q&A session, actually produced an average score that was more than 8 points higher than that for the group trained with method A. As you can see on the means, we have 56.5 on method B, and just 47.73 on method B. However, we need to know that if it cannot be assumed that the population variance are equal, a different formula must be used. So there's a test formula which are currently presented. So it seems to be a little bit more complicated than the previous one, but the same approach. We just need to identify the values of each of the statistical signs and substitute it on this formula to come up with the answer. Next slide would be on the using the computer to test hypothesis about the difference in two population means using the t-test. But since we have already learned how to manually compute it, I will just send you a link for videos and readings for the computation or how to calculate or to use the computer to test hypothesis. We'll just then go on the next subtopic on the confidence interval to estimate the difference between the population means, assuming the population variances are unknown and equal. So the formula is currently presented and it seems more complicated than the two previous ones. But the same approach, we just need to identify the value of each of the statistical signs and then substitute it to this formula to arrive at the answer. Let's take it for example. A group of researchers set out to determine whether there's a difference between average Americans and those who are phone survey respondents. Their study was based on a well-known personality survey that attempted to assess the personality profile of both average Americans and phone survey respondents. So table 10.3 already showed us the result. So the number 9 and 10 are the samples. Then the mean would be 37 and 34. And then the standard deviation would be 1.7 and 1.2. Then the degree of freedom was identified to be the sum of 9 and 10 less the constant of 2 equals to 17. So this 17 will be used on identifying the critical value of test, which is on the 17 and the confidence level of 99% as identified. We will be having a 2.898 critical value of t. Then all the values of the statistical sign will then just be substituted on the formula which we have presented and will give us a result of 2.10 plus minus 1.99. So if added, will give us 4.09. And if subtracted, will give us 0.11. So in here, the researchers are 99% confident that a true difference in population mean personality scores for conscientiousness between phone survey respondents and average Americans is between 0.11 and 4.09. Higher scores indicates more conscientiousness of phone survey respondents are significantly more conscientious than average Americans. So that's it on the hypothesis testing. What we just need to identify is to first to know the formula to be used, and then we just need to identify the values for each of the statistical signs and properly substitute it to arrive at the answer. The next topic would be statistical inferences for two related populations, which will be discussed by Sir Mark. Thank you.
Good morning, everyone. So the next topic will be statistical inferences for two related populations. Next slide. In this section, a method is presented to analyze dependent samples or related samples. This test refers to as the match pairs test. Others call it the t-test for related measures or the correlated test. Let's begin with the before and after study. Sometimes, as an experimental control mechanism, the sample person or object is measured both before and after a treatment. Certainly, the after measurement is not independent of the before measurement because the measurements are taken on the same person or object in both cases. Other example of related measure samples include studies in which twins, siblings, or spouses are matched and placed in two different groups. Proceeding on hypothesis testing, to ensure the use of proper hypothesis testing techniques, we must need to ensure that the samples must be dependent and sample size must be the same. Next slide. These t-test dependent measures uses the sample difference between individual matched sample values as the basic measurement of analysis instead of individual sample values. Analysis of the d-value sample differences in pairs effectively converts the problem from a two-sample problem to a single sample of differences, which is adaptation of the single sample means formula. This test utilizes the sample mean of differences and the standard deviation of differences, which can be computed by using formulas given in the slides. Next slide. As an example given in the slides, because no prior information indicates whether price-earning ratios have gone up or down, the hypothesis tested is two-tailed. Assume that differences in price-earning ratios are normally distributed in the population. In step 1 is hypothesize. Null hypothesis is to mean population difference equals to 0 and null hypothesis is to mean population difference is not equal to 0. And step 2 is testing. Since the data are related and assumed normally distributed, the t-test can be used. Next slide. In step 3, the value of alpha was chosen to be 0.01. In step 4, because, and this is to tell alpha equals to 0.01 and df equals to n minus 1 equals 9, the critical t-values is t 0.005 and 8 equals to plus minus 3.355. In step 5, the sample data are given in the table 10.5. Next slide. In step 6, the analyze the data. The table shows the calculations to obtain observed value of the test statistics, which is t equals to negative 0.70. Next slide. In step 7, taken an action because the observed t-value is greater than the critical table t-value in the lower tail, t equals to negative 0.70, t equals to negative 3.355. It is the non-rejection region. In step 8 is the business implications. There is not enough evidence from the value to declare a significant difference in the average price earning ratio between year 1 and year 2. The graph in the figure 10.9 depicts the rejection regions, the critical values of t, and the observed value of the t for this example. Next slide. Using the computer to make statistical inferences about two related populations, both Minitab and Excel can be used to make statistical inferences about two related populations. Figure in the slide shows Minitab and Excel output for the price-earning ratio problem. The Minitab output contains summary data for each sample and difference of the two samples along with a confidence interval of the difference, a restating of the tested hypothesis, the observed t-value, and the p-value because the p-value of 0.504 is greater than the value of alpha of 0.01. The decision is to fail to reject the null hypothesis. The Excel output contains the hypothesis, mean difference, the observed t-value of negative 0.70, and the critical t-values and their associated p-values for both one-tailed and two-tailed tests. Next slide. confidence intervals, sometimes we are interested in estimating the mean difference in two populations for related samples. A confidence interval for D, the mean population difference of two related samples can be constructed by algebraically rearranging formula given in the slide, which was used to test hypotheses about D. Again, the assumption is that the differences are normally distributed in the population. The following housing industry example demonstrate the application of formula given in the slide. The sale of new houses apparently fluctuates seasonally. In certain parts of the country, new houses sales increase in the spring and early summer and drop off in the fall. Currently presented are the formula and inputs we will be using to arrive at the answer. Next slide. The point estimate of the difference is D equals to negative 3.389. The confidence interval was determined to be 99%. Substituting all our values to the formula, we will arrive on the result of negative 5.625 and negative 1.153. The analyst estimates with a 99% level of confidence that the average difference in new house sales for a real estate company in Indianapolis between 2015 and 2016 in May is somewhere between negative 5.625 and negative 1.153 houses. And that would be all my report. I hope you have learned something today, and the next topic will be discussed by Sir Renz. Thank you.
We will now proceed with the discussion of Chapter 10, Topic 10.4, Statistical Inferences about two population proportions. Statistical inference is a process of using probability concept to deal with uncertainty in decision-making. It refers to the process of selecting and using a sample to draw inference or conclusion about population from which a sample is drawn. This is the Z formula for the difference in two population proportions. This symbol is a sample proportion. This is the sample size. This is the p-value or the probability of success. And this is the probability of failure. Therefore, in this formula, sample proportion 1 is a proportion from sample 1. Sample proportion 2 is a proportion from sample 2. Sample size 1 is the size of sample 1. Sample size 2 is the size of sample 2. P-value 1 is the proportion from population 1. P-value 2 is the proportion from population 2. And this is a probability of failure 1, and this is a probability of failure 2. The previous formula requires knowing the population proportions. Since the population proportions are generally unknown, an estimate of the standard deviations of the two population proportions was used, where, in this case, this formula was applied. To show the formula in an example, a group of researchers attempted to determine whether there was a difference in the proportion of consumers and the proportion of CEOs who believe that fear of getting caught or losing one's job is a strong influence of ethical behavior. In their study, they found that 57% of consumers said that fear of getting caught or losing one's job was a strong influence on ethical behavior, but only 50% of the CEOs felt the same way. Data were determined from a sample of 755 consumers and 616 CEOs. Does this result provide enough evidence to declare that a significantly higher proportion of consumers than of CEOs believe fear of getting caught or losing one's job is a strong influence on ethical behavior? Let us now digest the example in a step-by-step process. Step 1. Let us determine the null hypothesis and the alternative hypothesis. Step 2. With large sample sizes and unknown population proportions, the previous z-test is appropriate. Step 3. Let A, or the significance level, be equal to 0.10. Step 4. For a one-tailed test, the critical z-value for an A level of 0.10 is 1.28. Step 5. Gather data. Step 6. With all the available figures that we have, like the population size of the consumers, the population size of the CEOs, the result of the surveys, and plugging in those data into the formula, we can now make the calculation. And from there, we can identify the rejection region. Step 7. Because this test statistic z is equal to 2.59 is greater than the critical value of z 1.28, reject the null hypothesis. Using the p-value method for z 2.59, the p-value is 0.0048. Since this p-value is less than a is equal to 0.10, reject the null hypothesis. And from there, we can make a conclusion that a significantly higher proportion of consumers than that of CEOs believe fear of getting caught or losing one's job is a strong influence on ethical behavior. Let us see another example of checking confidence interval to estimate proportion of population. Suppose that, in an attempt to target its clientele, managers of a supermarket chain want to determine the difference between the proportion of morning shoppers who are men and the proportion of after 5 p.m. shoppers who are men. Over a period of 2 weeks, the chain's researchers conduct a systematic random sample survey of 400 morning shoppers, which reveals that 352 are women and 48 are men. During this same period, a systematic random sample of 480 after 5 p.m. shoppers reveals that 293 are women and 187 are men. We should be able to construct a 98% confidence interval to estimate the difference in the population proportions of men. Let us now gather the data. We have the number of morning shoppers and the afternoon shoppers, the population size, and the number of men and women for both data sample. We can now supply the given values into the formula. In here, we can see that there is a 98% level of confidence that the difference in the population proportions is between distribution 0.334 and 0.206. You can also use computer to analyze the difference in two proportions. Minitab has a capability of testing hypotheses or constructing confidence intervals about the difference in two proportions. Let us now talk about testing hypotheses about two population variances. Difference in variances is used as a measure of relative risk, like in finance, or comparison between processes, like in manufacturing. Here is the F-test for two population variances. Please note that the ratio of two sample variances follows an F distribution, and the population must be normally distributed. Suppose a machine produces metal sheets that are specified to be 22 millimeters thick. Because of the machine, the operator, the raw material, the manufacturing environment, and the other factors, there is variability in the thickness. Operators are concerned about the consistency of two machines. To test consistency, they randomly sampled 10 sheets produced by machine 1 and 12 sheets produced by machine 2. They assumed that sheet thickness is normally distributed in the population. We will now test to determine whether the variance from each sample comes from the same population variance or from different population variances. To test the hypothesis about two population variances, Step 1. Determine the null hypothesis and the alternative hypothesis. Step 2. Since the population is normally distributed, the F-test for the ratio of the variances can be used. Step 3. Let A, or the significance level, be equal to 0.05. Because we are conducting a two-tailed test, the significance level will be 0.025. We can then supply in the formula the available values like the variance and the sample sizes to get the degree of freedom numerator and the degree of freedom denominator. The critical F value for the upper tail is 3.59 and the lower tail value is computed as 5.62. The final conclusion will either be to reject the null hypothesis or to not reject the null hypothesis. That concludes our report. Thank you for listening.
Created using Powtoon.